Okay, I think it's slowing down.
Agreed.
Great. Okay, well, thank you everyone for joining us. In case you're a little bit lost, you're at the 2024 Geo-Launchpad and RESESS Lightning Talks. I am Anika Knight, and also here with me is Kelsey Russo-Nixon. We lead these programs. So before we start, we're going to start with the ERSCOPE Code of Conduct. As participants in this meeting, we do have expectations of you and everyone else participating. Please treat everyone with respect and consideration. Value the diversity of views that are going to be presented to you here today, or you might see in the comment section. Please be considerate, inclusive, respectful, and also collaborative. Please be kind, avoid personal attacks. Communicate openly with respect to others, critiquing ideas rather than the people themselves. Be mindful of your surroundings and your fellow participants. Please respect these rules, other policies, and also please communicate professionally with the audience. We all have different backgrounds. Please do not insult or put down others. I'm also going to acknowledge the land that we're all on. So as ERSCOPE Consortium and the NSF's Gauge and Sage facilities, we really are global. We would like to acknowledge the generation of peoples and communities that have been and will always continue to be the stewards of the land that we now use for our work. We ask that you join us in acknowledging their communities, their elders, both past and present, as well as future generations. This acknowledgement is just one small part of our commitment to dismantling the ongoing legacies of settler colonialism. If you would like more information, you can see where our notice stations are as they relate to Indigenous territories, and just more information on historical territories of Indigenous nations at the QR codes located here and there. So, first program, Geo-Launchpad.
So Geo-Launchpad is a program specifically designed for community college students. It's currently geographic limited in that we accept students from Colorado, New Mexico, and Wyoming. And the goal of this program is to get students an introduction to research, kind of what does a research project look like, as well as what careers in the geoscience look like. And so the difference really between Geo-Launchpad and RESESS, besides where they're at academically, is really just that they're doing research support projects. So not necessarily an individual research project, but gaining an opportunity to get those skills and get them research ready. I'll just say that this year we had 6 students in the cohort, them pictured here, at their first week of orientation down at the University of New Mexico in Albuquerque. And they came from all different schools. So we had lots of different schools represented this year in Colorado and New Mexico.
Our other program is RESESS. It stands for Research Experiences in Solid Earth Sciences for Students. It's a 1 to 2 year independent summer research internship program that's focused on earth science. This year, our goal was to have over 50% of our interns focusing on geophysical projects, which I think we well exceeded, as you'll see in our presentations. The program is dedicated to providing an authentic research experience as well as increasing diversity within the geosciences. So highlights of our program, we focus a lot on career and scientific advancement skills. So this starts with a week of orientation. This year, we are at the University of New Mexico. We did field experiences where students were getting hands-on experience with different instruments, seismic and geodetic. They also got a lot of team building activities. We did some computer work with them. It was just a really great chance for everyone to be together to partake in things in the geoscience world. We also have a scientific communication and writing class that all students are instructed to do over the summer. We talk about the different parts of scientific communication as it relates to papers and posters, focusing more on posters. As undergraduate students, that's most likely what they're going to end up doing when they go to a conference. Also, there's different levels of mentorship. They have the program leads, they have their scientific mentors. Many of them also work with graduate students. We have field trips over the summer that's mostly related to where they're working for the summer, but also while we're in person during orientation week. And then if interns successfully complete our programs, they are funded to participate in a national science conference. Most of the Geo-Launchpad interns will be going to GSA this year, and all of RESESS will be presenting their work at AGU this fall. And their abstracts are all in. So if you're attending any of these conferences, please stop by and see our interns. So our interns, this year we had 22 interns with no repeat institutions, which is really impressive for us. It really speaks to how far out we're going to advertise our programs and who's actually applying. So here's little logos from all of them. Funding, none of this could be possibly done without the National Science Foundation. We are funded through several grants. The first is Gauge. So our facility does fund the good portion of our recess interns, as well as many GLP interns. Some of the recess interns are also funded under RU grant. So as EarthScope, we combined two independent research internship programs into one program under the title Recess. So if you're familiar with what was known as URISE or the IRIS RU program, that's now under the large umbrella that is Recess. GLP was also funded under GeoPaths grant, and this was the final year for that grant. Additional support. So many people go into helping us run these programs. It cannot be done by us alone. First, the recess mentors, the research mentors, the GLP mentors, our graduate assistant, other staff who have helped. Barbara Reynolds helped a lot with administrative support, all of engagement, the business affairs team, IT team, our compliance team. Truly everyone at EarthScope helped us kick these programs off. And different for this year for Recess under its title is we had many different cohort locations rather than having interns in one or two places. We had a cohort at New Mexico Tech. We had 8 interns based there. We had interns at the University of Colorado Boulder. We had interns at Florida International University. We had interns University of Alaska Fairbanks, Sandia Labs, University of Kansas, Caltech, and Penn State. So cohorts of interns everywhere. So that brings us to our agenda for today. We have 8 presentations for you all. They should all be about 5 minutes with a few minutes for questions after. We ask that if you have questions, hold them for after, or you put them in the chat and we will get to them. So kicking us off is Dulaney. Dulaney is a recess intern who is based at the University of Alaska. I will stop sharing, and Dulaney, whenever you are ready, you can share.
Hi, everybody. I'm Dulaney Boonsue. I am a student at Western Carolina University, and I'm going to be presenting here. I'm just going to share my screen. Can everybody see it? Oh no, it's doing the weird screen sharing is paused.
So then stop sharing and reshare just the going slides.
All right, let's try this again. Okay, did it work?
One second.
No worries. I am going to share my desktop and I apologize for everything, but the goal is to get to the slides here. How about now?
Perfect.
Yeah, that's great.
Great. Okay, so as I said, my name is Dulaney Boonsue. I am working with the University of Alaska Fairbanks this summer, but I attend Western Carolina University under 2 amazing mentors this summer, and we have been exploring the role of gravitational load on deformation at Westall Volcano at Unimak Island in Alaska. Now, to get into it, we have been wanting to understand volcanic behaviors as a whole, and by a great way to do this is over time modeling deformation. Now, deformation at the surface provides a lot of information related to the state and activity levels of a volcano, and models like this are often used to invert surface deformation to determine source parameters. So looking at the plumbing system of a volcano and being able to there model the deformation at the surface. So it is a forward approach to a holistic issue. Now, one of my coworkers, Isabel Twomey, she is doing the inverse modeling where we come together from 2 ends of the spectrum and connect in the middle. Now, this model has been done before, but with the addition of load, we are creating new parameters and incorporating new ones that have not been incorporated before due to various, reasons of it's hard and complicated. And so this is something new. So familiarizing myself with new concepts, variables, and COMSOL was a huge part of my internship's beginnings. I had to come in, I don't have a geophysics background at all, and so it was a lot of learning to get myself where I am now. A lot of this was researching other people's work and papers, and here on the right, we have a figure based on Browning et al. 2021, where I went through what they had found and discovered in their parameters, and I was able to recreate the figures that they had present in their paper. This was a great way to like learn about COMSOL and just the, I guess, technology I'd be using. So to further what I took from Browning et al., I used Mario and Grieda's work, and that group's work from 2024 to work on Westall's parameters. Now, this included taking a pressurized spherical source that was 7 to 8 kilometers deep and was inflating. So by doing this, we created these models that represented different stress states, so that we might be able to see deformation on the surface as a whole. Now, this top figure, figure 4 here, is the first principal stress, which is essentially the tensile stresses. So thinking more lithostatic as a whole and what the Earth is demonstrating just on this cavity or chamber entirely. If you go down to figure 5, that is the von Mises stresses, which is a shear stress, which is adding an additional force, which kind of creates a different dynamic within this displacement field that we're seeing. Figure 6 is the same von Mises stresses, but with the deformation modeled. You can look at the top of the model there, and there is a kind of ridge line, and that is the deformation we're seeing now. This is magnified 1,000 times of what you would see. You'd only see a few centimeters per year, but it's what we're looking for to be able to see a deformation at the surface when creating these models. Now, the ultimate goal with all of this is to incorporate that load factor. By adding the load, we're going to see if Westall's deformation is influenced by these seasonal changes. It's glacier capped, as well as edifice growth from eruptions, the most frequent being from 1991 and 1992. And these additional factors are going to show a more realistic expectation of how deformation is moving and changing the landscape. Of course, this is always helpful for local populations and air traffic safety things that are just very valuable. And we hope to recreate these with all 3 of the major volcanoes on Unimak Island, including Fisher Caldera and Shishaldin. These, in retrospect, will all be able to create models that are showing a culmination of possible interactions between them as well, which just gives a broader understanding of what's going on in the island. But that will be carried on by the team, and I have been super happy to be a part of this. So thank you guys. If there's any questions, I can also answer those now.
Great job, Dulaney. So if you have any questions, you can put them in the chat, or you can raise your hand and ask. I have a question. So you've learned a lot on this. You did a lot of studying in the background. Is there anything that you would do differently if you were starting this again tomorrow? If it was like clean slate, start new. Is there something that you would change?
I would love to take more geophysical classes to understand the concepts better as a whole. I feel like I came in a little bit unprepared because I'm simply a geology student and I really don't have that much background there, but I would love to learn more, and then I've been able to better understand some of those concepts coming into it.
That's fair. Cool. Michael?
Great presentation and nice to see all of your progress over the summer. So a follow-on question to Anika's then is, will this influence the courses that you maybe consider for electives and things going forward in any way?
Yes, I have actually already looked into that. My university offers geophysical courses, but I do believe you have to be a physics major and they're kind of up there. However, that doesn't stop me from doing any side work or other understanding with professors on the side. There are many opportunities to grow my knowledge, and I believe that there are other ways to do that other than just elective courses.
Great.
Moira wants to know, what was your favorite part of this experience?
This experience took me to a lot of different places. I was working with the University of Alaska Fairbanks and got to live there for this summer. And the opportunity to not only explore somewhere new, but also to be learning a very different concept than something that I'm on track with in school has been an amazing opportunity that I wouldn't trade for the world.
Thank you, Dulaney. Okay, up next we have Izzy.
Okay, hi. Let me share my screen. Does that look like a presentation to you guys?
Beautiful.
Okay, great. All right. Hi everyone. My name is Isabel Twomey. And I am going to be a junior at Wellesley College this year, majoring in geoscience and astrophysics. And this summer, like Dulaney, I was also here at University of Alaska Fairbanks working with the Geodesy group in the Geophysical Institute with our two amazing mentors, Revathi Parmeswaran and Ronnie Grappentine. And my project this summer was modeling deformation for Westall Volcano on the same Unimak Island. So our project, the big picture of what we're doing is modeling volcanic systems, which on the large scale helps us understand volcanic processes and how volcanoes work, but also understand associated hazards and be able to provide resources and information to communities. Specifically, my work is part of a 2-year project on the interactions of volcanoes on Unimak Island. And so, as Delaney said, that includes Westall, Fisher Caldera, and Shishalden. Me specifically, I was looking at Westall, looking at the surface deformation between 1992 and 2009, which will play a role in the larger historical understanding once we have kind of looked at each volcano individually. And my goal with that is to quantify the deformation at the surface and then use that and our knowledge of geophysics to work backwards to understand what's going on underground and what the volcano's plumbing looks like underneath the surface. So my data comes from INSAR observations from ERS-1 and ERS-2, which are two satellites from the European Space Agency. And so what I'm doing with this data is I'm essentially looking at radar images and looking at the difference between two dates and times and using that to judge how much the land or the surface of the ground has moved or changed. So the basic way that works is the satellite does multiple passes over the same site, so multiple repeat orbits, and you can pick two specific images or scenes and then look at the difference between them. And so specifically with INSAR, we're looking at phase, which is just has to do with the wavelength of the microwave signal we're sending. And so we're looking at, has that changed? Has the signal the satellite is receiving changed between passes? And if so, that would tell us there has been some deformation. And so taking that data, the goal is to do 3 separate processing steps to finish the project. So the first is GMT SAR, which is a part of the generic mapping tool. And so I'm using that to create interferograms, which is essentially mapping that like color mapping that deformation, so you can look at it visually, but also that contains numerical data as well. And so I've done that for a lot of different pairs, scene pairs for the 1992 to 2009 period. And then the second step is using MintPy, which is another software package, and that is used to combine the interferograms from all the individual pairs and to put that all together to create one time series that captures the whole 20-year period. And then the final step is to use VMod, which is short for Versatile Modeling of Deformation, which is, again, another software package. But this time is to use that quantification from the time series and to invert that, again, with our knowledge of physics to understand what might be going on underneath the surface. As I said before, this is part of a larger 2-year project, but where I'm at, what I've done so far is I've gotten through the data and completed the GMT SAR processing. So I essentially have, there's an example here of interferograms, but I have a bunch of these for quite a few different pairs. So the ones shown here are images from 1992 and 1993, and we're looking at the difference between them. So on the left, we have what is called a wrapped image, which is showing the change in terms of phase. So that's why the units are radians, versus on the right, we can see the change between these two dates in absolute measurements compared to a reference pixel. And so that's in terms of millimeters of subsidence or uplift in the line of sight that the satellite's looking. And continuing on from when I leave, there will continue to be work in MintPy and in VMod. I'm currently working on some MintPy processing, and the group after I leave will continue with these steps. And so, yeah, that's what I've been doing this summer. And thank you all, and please let me know if you have any questions.
That was great, Izzy. Okay, if you have questions, same deal. You can put them in the chat or unmute yourself and ask them out loud. Yes, Michael.
Thanks for sharing your project. So I have a question that ties into something else that I happened to just be working on before this. So it looks like you spent a bunch of time in GMT for this summer. Had you had prior experience working in GMT before your internship?
No, when I got here in June, I didn't know what that was. Definitely spent the first couple weeks trying to figure that one out and navigate that.
So then the follow-on question I have is, what type of resources would have been helpful for you to get ramped up using GMT, relatively quickly?
Yeah, I think I didn't have a lot of background in any kind of computer skills or coding, so I think a working knowledge of just like using terminal and basic like Python scripts would have definitely been helpful of that. I'd also never worked with like geodetic data, so I didn't really know what INSAR was or what deformation was. So kind of having more of a background, I think it was something that I got once I got here, but those could have definitely been supportive of that process.
Great, thank you. That's helpful feedback for us.
Izzy, Marah would like to know, what did you find most difficult about this experience?
What did I find most difficult? I think one kind of touching on what I just talked about was learning a bunch of new software systems, which as I've learned while I've been here, all the files and everything has to be set up in a super specific way, and it won't work if it's not. So a lot of my time here has been spent trying to figure out where the error messages are coming from or why I can't get them to go away. And so that has definitely been challenging, but also pretty rewarding once kind of when you make progress with those.
Yeah, that's fair. Okay, thank you, Izzy.
Yeah, thank you.
Up next, we have our first Geo-Launchpad presentation, Joe Ray. If you would like to share your screen.
Right. Okay. Hello, my name is Joe Ray Bermudez. I'm a student at Central New Mexico Community College. My mentors are Evan Owens and Virginia McElmore. The research conducted was a comparative analysis of laboratory and portable X-ray fluorescence methods for the Guyanus Mountain rock samples. Background: the Guyanus Mountains are part of the North American Cordilleran Belt of alkaline igneous rocks and located within the Licking County Porphyry Belt of central New Mexico. The district was first explored in 1870 for gold and silver. The Guyanus Mountains contain rocks of the Proterozoic and Quaternary ages. Within the mining district are base metals, copper, lead, zinc, and rare earth element-bearing fluorite, barite, and bastonicite veins, and breccia. The purpose of this experiment was to determine whether PXRF, portable X-ray fluorescence, can be used as a screening device for critical minerals. 2, to test the PXRF's ability to provide reliable, quick, and quantitative elemental analysis for exploration geology. And 3, to reduce the need to send preliminary rock samples to a geochemical lab. The method used was to scan powdered rock samples from areas in the Guyanus Mountains containing high levels of critical minerals with the PXRF. Then to compare the PXRF elemental analysis with lab geochemical data set. And lastly was to utilize bivariate plots to determine correlation between analytes. So my results and discussion. These are some bivariate plots showing PXRF data versus lab data. A slope of 1, y equaling x, means that the PXRF had a positive correlation between lab analytes, and the best slope is 1, and with y equaling x. And so the R squared value indicates how well the data fits in a linear relationship, and a perfect linear relationship would be R squared equaling 1. For some of the analytes, the PXRF over measured, and those were sulfur, calcium, titanium, and zinc. And for some analytes, it underreported, and that was yttrium and potassium. Titanium yielded poor results due to peak overlap of the X-ray characteristics of titanium and barium. And so the device only picks up titanium, it doesn't pick up barium, so it got those confused. The best performing analyte was strontium with a slope, an R squared value of 0.97 and a slope of 0.99. Okay. My conclusion was that the PXRF is capable of positive correlation between base metals, sulfur, and yttrium. Yttrium was plotted against total rare earth in the data set, and with the R squared of 0.97 shows a positive correlation, demonstrating that yttrium can be used as an analog for rare earth elements in the Guyanus Mountains. But the final results were, unfortunately, the PXRF cannot detect barium, fluorine, and rare earth elements, and any elements lighter than phosphorus, making it of limited value in the Guyanus Mountains at this time. And so that is all. I can take any questions or comments.
That was great. Questions for Joe Ray? I have a question. What attracted you to the Geo-Launchpad program? Was it geology in particular because you know you love it, or is it just something that you're interested in like branching out into?
Geology is hopefully will be my major, so that really interested in me in it. And for my first geology class I've taken, we had another gentleman that was in the program, and he gave us a slideshow on his experience. I think he was a geographer, and he told us about the experience everyone had in Socorro, and he mentioned that some people were part of the economic geology department and they were working on carbonatites in the Lematar Mountains, and that really interested me. And I had a really good geology teacher that really pushed me to go for the internship. And as time went down and I talked to Kelsey for the interview, it just all worked out, and I'm so grateful for it. I've learned so much over this summer. I know more about what geoscience means, and it's way more diverse than I thought it was. I thought it was only about rocks and minerals, and I got to learn about how seismology works and volcanoes, and got to see how spectroscopy works and different methods of testing in the lab. And so if all goes fine, I would love to get um, into geochemistry. That would be really cool. Hopefully.
Cool, thank you. Any other questions for Joe Ray? Moira has great questions today. Says, I loved it. What knowledge did you gain from this experience?
That is a good question. So much, an exponential amount of knowledge was gained. Like I said, I didn't know how involved the geology was. I was always a mineral collector and rock collector, but I didn't know that there's so many different applications for it. And this summer, I really got to see that at the Bureau, about how many people work on finding critical minerals, elemental analysis, volcanoes. And yeah, it's just a huge experience. I feel in this time of 2 months, I learned probably more than I've known about geology. Thank you, Marah.
Shelley?
Yeah, hi, Joe. Thank you for your presentation. It was really good, and really excited to see an instrument that could possibly, save sending samples to a lab. And even though it can't identify everything to the accuracy that you guys were looking for, is the technology component of any interest to you, like how to make that instrument better, or maybe other potential applications, like you were saying, geochemistry, other tests that you could make, like while out in the field, because hauling those samples and shipping them off, and it takes sometimes weeks and months to get those results back.
Yeah.
So just curious if you're interested in the technology part as well as the geochemistry, or, what you could see as future paths there.
Yes, thank you, Shelley, for the question. Yeah, I'm definitely interested in the technology aspect. I think when I was researching that the first portable X-ray fluorescence devices were made, I think, in the 1970s, but they were so large and you needed so much equipment for them that it wouldn't really be applicable in taking it into the field. My research was done on powderized samples that weren't whole rock samples, hand samples. So I would like to see if the technology goes forward to where it can be precise for whole rock samples, and maybe if there is a way to figure out how they can get those other elements in there. I think one of the major problems with it that my mentor was telling me is that the elements above phosphorus are so light that the instrument gets confuses the air. So a thing that's problematic is trying to figure out those elements without using a vacuum. but I am interested in how far it goes, and if it can be utilized by common people at one point if the technology gets, um, cost effective enough and portable and usable to all people that maybe everybody could have one on their phone someday or something like that.
You're making me think about how to have a portable vacuum chamber. Yeah. Well, thank you. You obviously learned a lot throughout the summer, and the economic component, even though if you that's not where you end up going, there's definitely a big application there. So thanks so much.
Yes, thank you.
Okay. Thank you, Joy. That was great. Up
Thank you.
next, we have recess intern Sam.
Hello, everybody. Give me one moment while I share my screen. Can everybody hear me?
Yes, we can hear you.
Okay.
Joey, if you could stop sharing, that'd be great. Thank you.
All right. Okay. Hello, everyone. My name is Samantha Beauchaine, and today I'll be talking to you all about my research on the characterization of a eudilite vein in the Bermudez Mountains, New Mexico. I think it's important to note some background on the Bermudez Mountains and eudilite before we dive in. So for your knowledge, the Bermudez Mountains is a mass of tertiary intrusive bodies located along the North American Cordilleran Alkaline Igneous Belt in southern New Mexico and northern Texas. For this project, I was studying a eudilite-bearing nepheline cyanide that was identified within a boulder of contact metamorphosed carbonate adjacent to the Wind Mountain nepheline cyanide intrusion in the Bermudez Mountains. Eudilite is a complex zirconosilicate mineral. It can contain rare earth elements such as cerium, lanthanum, neodymium, and yttrium, which are crucial in various technological applications, including electronics, magnets, and batteries. For my research of characterizing the eudilite vein, I used a number of methods, including optical petrography, PXRF, BSE, WDS, and XRD. So to start off, I started with optical petrography. So a slab was cut from the boulder that was found, and from the slab a thin section was made. With this thin section, I first began to look around and see what I could discover. The few things that I could confidently identify were nepheline, adrian, and eudilite. So after that, I moved to the next step in my characterization journey, which was utilizing the PXRF to get some elemental composition of my vein. I analyzed 15 spots on the slab and transferred the data into IOGAS, just so I can see a plot. So as you can see in step 2, you can see that within the vein, there's zirconium and niobium. In the selvage, which is the surrounding area of the vein, iron, and in the host rock, calcium. So if we go back for a second to what I spotted in petrography and the background information, eudilite is a zirconosilicate mineral. So seeing a zirconium in the vein was a good sign for me. The next stop was the electron microprobe analysis. Here we used a focused electron beam to excite X-rays in small areas in the thin section to determine their composition. As you can see in step 3, I focused on the same areas that I looked at in the petrography stop. Here I was able to identify the minerals I wasn't too sure about, and when looking at the thin section, using the optical petrography. So one thing I noticed while looking at the minerals with the electron microprobe was that a lot of the eudilite minerals were two-toned. So if you avert your eyes to the next step, you can see a zoomed in image of the eudilite mineral with a light gray side and a dark gray side. I added a line for your convenience because it's a little difficult to see the difference in the image. I picked a eudilite mineral with not as many fractures and ran a transect across it. We did 16 points across the mineral, with the first 7 representing the light gray portion and the remaining 9 representing the dark gray portion. As you can see in the graph, going from the light gray to the dark gray, there's a decrease in niobium and manganese and an increase in iron. So the last stop in my characterization journey was to get our slab's fingerprint using powder XRD. I split the slab into 5 parts, 3 being the host rock, 1 being the selvage, and 1 being the vein. Here you'll see in the last step, the XRD results from the vein, which contains analcyme, fluorapatite, nepheline, and the eudilite group icronite. Okay. So after my last stop of characterizing the eudilite vein, I came to a few conclusions. One, that the sample is an alkaline skarn based on the chalcosilicate minerals that were found. Two, based on the powder XRD and the electron microprobe analysis, the eudilite sample belongs to the aqualite icronite series. Three, rare earth values from the vein were measured up to a value of 0.56 weight percent total rare earth elements oxide. And last but not least, the rare earth elements were found to be dominantly present in the eudilite group, the aqualite icronite series. Thank you.
Great job.
Thank you. Any questions?
The floor is open for questions. You're getting towards the end of your degree.
Mhm.
Has this shaped what you're thinking about doing next?
100%. I was a little, I don't know, I guess when you get towards like the end of school and like getting ready to graduate, I'm like, what am I going to do with my life? And so mining was something that intrigued me. So working with Ginger was very eye-opening, like seeing what she did and everyone on her team did. I was just like, this is where I belong. This is what I'm going to be doing in the next step of my life. So yeah, it did.
Cool. Moira would like to know, what are you most proud of accomplishing within this internship?
Oh man, I think a couple things. One, facing my fear of public speaking. Yeah.
You did a great job.
Oh, thank you. Still trying, and also just, I guess, being confident, like I can do this. I think you kind of doubt yourself when you're doing things like this. Like when I first got into the internship, I was like, am I smart enough? Am I like imposter syndrome? Like I overcame that, and it just meant a lot to me personally. Like, oh, I'm actually smart enough to be here. I can do this.
Hey,
thank you, Moira.
Yeah, you're all smart. We wouldn't have chosen you if we didn't think that you could be successful. Okay, thank you, Sam. Great job.
Yeah, thank you.
Up next, I believe we have Caleb, not recess intern, GLP intern Caleb.
Hi, Kelsey, are you still able to?
Yep.
Awesome, thank you.
I am, no problem. Give me just a second. Okay.
Hello, everybody. My name is Caleb Regier, and I study the geochemistry of critical minerals in the Copper Flat tailings of Hillsborough District, New Mexico, in the Copper Flat mine. I worked with the New Mexico Tech and the Bureau of Geology under Virginia McLemore and her team of grad students. Next slide, please. The Copper Flat Mine is a low-grade copper in sulfides, in a matrix of quartz and feldspar. The previous production in this mine was in March to June of 1982, when Quintana Mineral Corporations produced copper, gold, molybdenum, and silver before declaring bankruptcy. Current work is that the TMAC Resources Group is acquiring permits to reopen the mine, as well as many research projects have been completed in the area.
Thank you.
Most of the world's copper is mined in open pit, by open pit from porphyry deposits, generally large, low grade, from a magmatic hydrothermal ore deposit. In this case, from a volcano. And then tailings are materials discarded after the milling process and ore minerals and trace minerals are extracted. The extraction of these critical minerals in the tailings for the copper flat mine could be economically viable due to the nature of reopening the mine and how the tailings were deposited in the first place. Next slide, please. Our largest method of analysis was using a portable X-ray fluorescence machine. We compared those to whole rock geochemistry data from a lab and determined some pretty cool things. So here I have a graph with copper versus my lab data. My lab, I have my dotted line here showing the trend line that the copper versus the lab data, the PXRF versus the lab data is showing versus a 1-to-1 line in that solid blue line. So we see a nice correlation between copper and the PXRF and a little bit more accurate at the lower levels of copper. I also did X-ray diffraction to determine the mineralogy of the tailings. We found quartz, orthoclase, muscovites, various clays, alunite, and calcite. The calcite at the surface, as well as the clays above 1.4 feet, show that there is possibly water, water reacting with the tailings on the top. We also ran our paste pH samples, paste pH on the samples we took, and they're showing very close to neutral. Most of them are above 7. There's one that is under 7, and in the non-acid forming group, well, most of them are uncertain. But we see minimal signs of acid rock leaching among the samples. Next slide. Here I also have a series of graphs showing our downhole tailings profile. I have copper, total rare earth elements, yttrium, sulfur, and zinc, all showing their parts per million against the depth on the side there. And we see a nice correlation as we go down, especially with copper. As we lower in the pit in the tailings profile, we see more copper. My initial conclusions are that PXRF is good at detecting copper, but once you go over 300 parts per million, it starts underestimating it, which could potentially be good. I mean, if you scan it and you have copper there, you can reasonably be sure that there's more than what the machine is telling you. The pH values are close to neutral, suggesting that there's not high evidence of oxidation. And then copper generally increases with depth within the tailings profile. Next slide. Here are my acknowledgements and references. I would like to thank Virginia McLemore and her team for their continued support through this project. Does anyone have any questions?
Good job, Caleb.
Thank you.
Okay, let's see. Moira would like to know, I know you love archaeology. Did this spike your interest in a more geo-focused career?
Absolutely. So I've been talking a lot about a geoarchaeology profession, kind of combining the two to study like mineralogy within, artifacts. And I've been looking into schools and seeing what kind of coursework I would need to, branch into that aspect of archaeology. Besides that, the PXRF machine has come out a lot within archaeology work as a whole because you don't need to destroy the sample to use it. And specifically in obsidian sourcing, it's a really good way to kind of find out where obsidian came from. So yeah, I feel like I learned a whole lot of really useful skills in both geology and archaeology.
Cool. Any other questions for Caleb? Shelley.
Hi, Caleb. Uh,
Hey.
Great presentation and really exciting. In a way, you were doing archaeology by looking at those drill holes going through the tailings.
Yeah.
And I was curious, both from a personal and then a kind of a work question, like how old were the tailing piles at the end and
Okay.
versus the top?
Yeah, the tailings profile all came from that 3-month period from March to June. So the oldest in the piles was from March, and then the youngest was from June. They only produced for those 3 months and then declared bankruptcy, and there's been no further production at the site.
June of what year? This year?
1982, sorry.
1982. Okay. So, okay, that gives us some clues about, the oxidation rate
Right.
down to the bottom. And then, so you're looking at combining this geo and archaeology component. Where, what parts of the country are you thinking of, like for
Oh,
your following your
like,
degree then?
yeah, I would really like to study in the Southwest. I've been really interested in specifically Southwest pottery and ceramics. But hopefully Southwest, I've been thinking of schools in Arizona, schools in New Mexico, Utah a little bit. So I would really like to stay kind of localized here in the Southwest.
Yeah, great. Thanks again.
Yeah, absolutely. Thank you.
Great questions. Thank you, Caleb.
Thank you.
Up next, we have Geo-Launchpad intern Sammy.
Hello. Let me share my screen. Does that look okay?
Beautiful.
Wonderful. Let me make you guys smaller. Okay. Hello, my name is Samantha Koller. I currently attend Pikes Peak State College, and over the summer I was evaluating seismic noise in New Mexico seismic stations with Dr. Irby Basu. Next, please. Okay, so to begin, the New Mexico Tech Seismological Observatory has observed 702 earthquakes of magnitudes larger than 1.8 from 2001 to 2021. So in an effort to better understand these earthquake events and potential effects of background seismic noise, we aim to identify key noise sources such as anthropogenic activity, earthquakes, or other factors, and determine which stations were noisy and quiet within this region. So the first map that you see on the right-hand side is a map of earthquakes larger than magnitude 1.8 in the southeastern quadrant of New Mexico. As you can see, they kind of bunch together in these 4 distinct clusters. So the image on the right-hand side indicates the station locations that we used in this study. We tried to pick stations that were close to or within these different clusters. And we used 6 months of continuous seismic data. So our methods is almost identical to that of Robert Andrew in his 2022 study of background seismic noise across the continental US, in that we used Python codes to compute the power spectral density and create all the figures that you'll see presented in this presentation. From these figures, we were able to determine that stations located near cities were noisiest during the shortest period, which is 0.2 seconds. That stations that were further from cities but within known oil and gas extraction zones were noisier during the day. And most cities located near anthropogenic activity were noisier during the summer. The graphs you see on the right-hand side of this slide are called power spectral density probability charts, and they tell us the median noise data for each station that we looked at in our study. And then using that power spectral density data, we get these figures. So the maps that you see plotted at the top of this slide are median noise short period maps. So they take the median noise level from each station across 3 different time periods and plot them relative to each other. And when we look at these figures, we can see that the noisiest stations tend to be near cities or areas that we know have oil and gas operations. The diurnal variations map on the bottom left-hand side tells us whether a station is noisier during the day. So stations in red are noisiest during the day. And again, we see them near anthropogenic activity. The seasonal variations similarly indicates variations in noise level during the summer months, where red stations are noisier during the summer. And this trend seems to continue where there is anthropogenic activity and cultural noise. They're noisier during the summer months. So overall, we determined that stations are noisiest during the short periods due to anthropogenic, oil and gas, and cultural noise. And stations closer to industrial sites are noisier during the day. In the future, we hope to evaluate higher noise periods, study the other stations within this network, and conduct the study over a longer time period since we only used 6 months for this. These are the references that I used for my research. Thank you very much. I can now take questions.
Great. Moira was killing it with questions today. Says, great job. What did you find was the hardest thing in your research?
Definitely figuring out coding. I used almost entirely Python scripts for this project, and I had never used Python ever. So getting that to work and figuring that out was the longest part of my project, honestly. So I think getting over that hurdle was definitely the hardest. But once everything starts working, it's like super easy. So
Keeping up with that, are you going to take some classes? Like, has this impacted what classes you're going to take this fall or next spring?
yes. Well, I'm actually considering minoring in computer science since coding seems to be such an important tool in many different areas of geoscience. So that's something that I'm considering. And I'm also taking a Coursera course in GIS systems as well. So, yeah.
Great. Michael?
Thanks for the presentation. So one of the questions that I had as I was listening was, could you fit your research sort of into the bigger picture? So why are we interested in the noise sources in New Mexico for seismicity?
Yeah, so there's been an increase in actual earthquake events within that southeastern quadrant of New Mexico. So there's a real interest from seismologists in New Mexico to figure out what are the causes of these earthquakes and study them better. But because there's so much anthropogenic and cultural noise going on in the region, it makes it more difficult to determine what's cultural noise and what's an actual like earthquake event. So by looking at these stations and figuring out, okay, which stations are noisier than others? Why are they noisy? What are the sources of this noise? What patterns are we seeing? That can better help seismologists when they're looking at seismic data from these stations and other stations in the region to see, okay, are we looking at an actual seismic event, or is this just like trains going by and daily traffic and things like that?
Great, thank you.
Great. Thank you, Sammy. Great job.
Thank you.
Up next, we have RESESS intern Marah.
Hello, everyone. Let me share my screen with you. And we can get started. Hello, everyone. I am Marah. I'm going into
1
my.
second. Your slides aren't in slideshow view. Maybe stop sharing and
Oh,
reshare.
okay, let me do that. That didn't work either. Are they in slideshow view for you now?
No, I think it's about the screen that you're sharing. So leave your slides in slideshow view. Stop
That's
sharing the screen with
what I
us.
did.
Oh no.
Hmm,
One more time.
Okay. And mhm. Okay. Are they in slideshow view now? No. Okay, wait, I'm sorry.
Okay.
You could try what Dulaney did with sharing the whole desktop.
Yeah, let me try that. Okay. What about now?
Yes.
Beautiful.
Yay, great. Thank you. Hello, everyone. I'm Marah. I'm going into my junior year as an undergraduate at Mount Holyoke College. I am a chemistry and geology major there. Today, I'm going to be talking to you about the microseismicity analysis of the Valles caldera that I did, where we utilized passive seismic techniques as well as machine learning. And I'm also going to be talking to you about summer of applied geophysical experience. So let's talk about some background and goals. So my project was set in the Valles Caldera National Preserve, which is one of the National Park Service's newest members. It's the oldest of 3 young calderas in the US, the others being Yellowstone and Long Valley. And it's known for its quiescence and large amount of geothermal features in the southwestern portion of the preserve. And we had 6 broadband stations deployed from June to October of 2023 with the goal of gaining a more complete and comprehensive understanding of the Valles caldera's underlying structure to help identify zones of weakness so that we can better inform infrastructure planning and better assess hazards in the area as more and more people are walking through the park and preserve. Now let's talk about the data collection. So all of these stations were deployed by SAGE, or Summer of Applied Geophysical Experience. It's a geophysics field camp that's set in New Mexico where you learn how to deploy and use a variety of field methods. I spent 3 weeks of my summer at this field camp as one of my PIs. Akra Mostafanahad is one of the faculty members here. We deployed and collected data using gravimetric analysis, active seismic, passive seismic, ERT, which is electroresistivity tomography, and MT, which is magnetotellurics. Part of this field camp is also doing data analysis, but I won't be talking about that today. Now let's talk about the data analysis tools that I used for my research. The main tool that I used is Earthquake Transformer, which is a deep learning architecture-based machine learning software that is used in Python. The reason why we use Earthquake Transformer is due to its large detection range, it's open source, and it also does not need to have specific models for the area. We were able to use their general model, and as we don't have a large well of knowledge and seismic data for this region, we didn't have the ability to make a specific model. We used Earthquake Transformer for the detection and picking of seismic events, and I used OBSPI, which is an open source software, to do the earthquake data plotting and look at and create a seismic map. If you look at the figures on the right, this is just to show you the difference, or this is to show you the detection picking abilities of earthquake transformer. The heliporter at the top is the immediate detection and picking software without any further analysis or specialization of the data, while on the bottom, those events are picked after the phase association code of earthquake transformer has been run. And then I just want to talk to you a little bit about the data analysis process and what I did throughout the summer. So of course, first you have to collect the data, then do the detection and picking, and then this is more of the human part of this process. You have to look and review the events picked. I did this mainly by looking at heliquarter plots and seeing how well the events they chose matched up with the raw data. If you found this satisfactory, you can move on to the phase association and obtain a little bit more specified results. But if it wasn't satisfactory, you then look at the detection threshold parameters and refine them. I did quite a lot of refinement throughout the summer before moving through the phase association and mapping those seismic events to then visualize and analyze them. This is just, oh, there we go. This is just some of the test model parameters that I ran and the number of total events that were picked from it. So I did quite a lot of work on this to then find what parameters best fit the data that I was looking at. Before moving on, I'm actually still running new models, but we will continue with that and moving on. And these are just my acknowledgements and references. A special thank you to Anika, Akram, and Irby for helping me through this summer and through this process, and also to Barb, who helped us so much with my computer. So.
Awesome. Who has questions for Marah? Ooh, okay. Moira, just killing it with questions today. What skills did you learn from this internship?
Yeah, so I learned a lot of skills during this internship. I came into this internship with absolutely zero coding skills and was running Python and Bash codes and debugging them and creating some of my own as part of this, as I had to do I had to do some pre-processing of the data. So I learned Python, I learned Bash. I also learned so many field skills and how to deploy so many different types of field instruments and how to use field instruments. And as I kind of mentioned during stage, there's a data analysis component to it at the end, and I was on the data analysis of the electrical resistivity tomography team. So I also learned how to use Earth Imager software as a part of that. So just kind of a very wide variety of skills. I also learned a lot more about scientific writing than I had previously, and just geophysics in general. Almost the entirety of my background is in material science. And most of the research I've done previously was in aqueous polymer degradation. So there was a pretty big learning curve for me, but yeah. And then I'm going to answer James's question next because I see it. Sorry, Michael. But my perception of the Valles caldera before versus after the internship was I had no perception of the Valles caldera before my internship. Versus now, I know so much about it. I spent 3 weeks within the caldera learning about it, analyzing it, going through all different parts of the caldera. And it's a beautiful preserve, and it made me really appreciate the NPS a lot more than I had previously. Michael, you're up.
Okay, so these sorts of projects can involve lots of tedious seismograms and making picks in those. So what were your favorite podcasts or Spotify channels that got you through hours of picking lots of seismic data?
Yeah, so I will answer that, but also I want to say the reason, so Earthquake Transformer, looking at those models, it picks the data for me, which is what those different threshold parameters are. So I personally didn't have to like actually go through and like look at P and S waves and see if I could find that airwave or anything like that. Most of it was just debugging code. I did do some of that at the field camp looking at that active seismic data. But my favorite playlist when I was either waiting for my code to finish running or debugging code was probably, so I will say I listen to like everything under the sun, and my friends kind of like to harp on me about my playlist because my playlist is like days long, and just if I like a song gets added. So it's like classical music and EDM and classic rock and K-pop and whatever else is in there. I would say I probably listened the most to like Black Sabbath throughout that time. Yeah.
I love it. Thanks for sharing.
Yeah. Anika, I think you're
I
still
know, I
muted.
know. It's been 4 years of Zoom and still it happens. To cap off our presentations today, we have Recess Intern Juan, who's gonna present his work for us. Whenever you're ready, you can share.
I think it's this one. Nope. See my slides?
Yes, it looks beautiful.
Okay. Okay, so, whoops. Okay, so yeah, my name is Juan Cruz. I was a recess intern at CU Boulder this summer. I was working mainly with Daniel Giddens, but Catherine Materna also mentored me on code as well. So thank you to them for their help, and thank you to the NSF for funding my summer. I'll be presenting over rain and creepiness, evaluating the correlation between rain and creep events in California. Some background on creep events and creep meters. So creep events are millimeter scale seismic movements along faults that occur over hours to days. Only some faults exhibit creep, and even then, only some sections of those faults. So Southern San Andreas has locked sections and creeping sections. Creep events were first observed on the San Andreas in 1956 due to displacement between walls in a winery. And there are 3 proposed spatial extents of creep events shown by the image here with red triangles and blue areas. Those 3 sizes are short and shallow, long and shallow, and long and deep. I also included an image in the bottom left of kind of a schematic of a creep meter with the black line representing the fault. And the right image shows the creep meter and how it's installed on the fault. Usually they're installed only a few meters deep, and they just measure mostly at the surface, the creep shown by delta U. So there are 2 prominent theories that try to explain how creep events are triggered. The first one is the shallow kick theory, which states that changes to the surface from stress or pore pressure cause creep events, and these can be caused by either rainfall or atmospheric tides, for example, among other factors. The image there kind of shows the Mohr circle moving towards the failure envelope as the pore pressure increases. The other theory is the deeper slip patch, which states that a patch of rate weakening material causes local frictional weakening that then propagates to the surface. So my research was mostly focused on the shallow kick theory as I was looking at rainfall and creep events. And so Dan spent 4 months manually picking 5,000 creep events. So like he should have good answer to Michael's question about a playlist. But it spanned from 1980 to 2024. And I had to remove data from the Parkfield earthquake. So it's split into 4 regions along the San Andreas where creep meters are installed, which is Hayward, Parkfield, SoCal, and Hollister. And so the Parkfield earthquake in 2004 kind of provided a lot of noise in terms of creep events. So I removed like a 1.5 years of creep events. And then for the rain data, that came from the Copernicus Climate Data Store. And essentially, I spent most of my summer coding to where I just had to choose different parameters each time, and it'll produce a line plot. And so this histogram on the right kind of shows, in the next slide, I have line plots, and this histogram, the histograms here represent a point on each of those, with the observed in the brown, the by chance in the yellow, and the blue and represents the real. And so the by chance was that came from synthetic data that I time shifted the creep events yearly to preserve the seasonality of the rain. And so these were the results. So like I said, with the histograms, each of these points, for example, on Parkfield, this lighter blue line nearest to the top of the graph, each of those histograms represent one of these points. And so, yeah, the code takes a while to run, but it works. And so essentially what we learned is that different regions, the creep events at in those regions, they all show different relationships with rain preceding them. So Parkfield had what we determined were the wettest creep meters, which means that those creep events were preceded by rain more often. And then on the right-hand side of the screen, there's the southern San Andreas area, which had dry creep events, which meant that those creep events aren't preceded by rain as much. And Hollister was kind of a mix of the two. And so this kind of lends towards the idea that it's probably a combination of the two theories that are at play and not just one or the other. I think in the future, I would like to look at the differences between the creep meters, especially like the soil conditions that they're in, because I feel like that affects how the rain's percolating through the fault. And then these are my references. Thanks. Any questions?
Great job, Juan. Who has questions? What was your least favorite part about your research? Moira would like to know.
I'm probably waiting for the code to run. I've never had code take like days to run, so that was something new. I'm just having to like make sure my laptop, I don't know why, sometimes it would just like turn off or anything. It would just go to sleep, so I was just nervous. So like, oh, like maybe it hit an error and I'm gonna not even know because it's just sitting in the corner running. And so sometimes it was nervous. I was like nervous letting my code just run, but it worked. And I think that's pretty much the most annoying thing I had to deal with.
James?
Juan, great presentation.
Thank
My
you.
question is, what do you think you were going to find with your project versus what you end up finding? What I mean is, what, like, your results, did that surprise you? Or how did your ideas change through your project, if that makes sense?
So yeah, when I started the project, it was very exploratory. Dan first directed me towards like tectonic motivation for creep events. So I spent 2 weeks kind of coding for looking at local earthquakes in California. And that ended up not giving me any results at all. So going towards the rainfall though, I guess I expected it to be more apparent, like if rain was associated like higher percentages overall. So seeing the differences in regions was surprising. And then I have different plots. This kind of shows like an accumulation of rain with time, but I also have like looking at only 1 hour before, 2 hours before, so on, and then also have rates. So I'm still running code just because, like I said, it takes a long time to run. But so far, like the overall conclusions I've made seem to be pretty apparent. And then I also recently took into account evaporation and runoff, and I was kind of surprised it didn't really change the data that much in terms of results.
Thank you.
Thanks for the question.
There's a question in the chat from Christine. She would like to know, would you consider looking at borehole strain meter data? I recall the creep events showed up there.
Yeah, my mentor Dan, he looked at borehole strain meter data. I didn't get a chance to just because this was a big enough undertaking for myself, but I definitely would be curious to look at it in the future. I am a geophysics major at U of H, so maybe if I can convince a professor to let me work with some data or something, or like kind of sponsor my research, I would like to conduct further investigations.
Okay, thank you, Juan.
Thank
Did a
you.
great job. And honestly, thank you, everyone. Thank you, interns. You did great presentations. I know our audience learned a lot from you all. Audience, thank you for attending. Hope that you also appreciate our interns' presentations. This is also a reminder that our scope this year in terms of GLP and RESESS interns had 22 total interns. So this is just one of 3 presentations that we have for you all. Tomorrow, please join us back here at 10 a.m. Mountain Time. 10 a.m. Mountain Time, we'll be doing more presentations. And then again on August 15th, when we have even more presentations for you all to see. But if you have like follow-up questions for the interns, you can email Earthscope at internship@earthscope.org and we'll get back to you. Also, the interns made LinkedIns this summer, so you can also find them on LinkedIn or at fall conferences this fall. Okay, thank you everyone for your time. I hope that you all have lovely afternoons and evenings, and I hope that we will see you again tomorrow.
Great job, everybody.
Great job, everyone. These are also recorded in case you missed a presentation. You can catch them on YouTube later.